Welcome back. This is lesson 9C, where we're going to calculate amounts using balanced equations, and the work is covered on page 201 to 203. I'm going to call this mass volume calculations because either a mass or a volume of one of the reagents are given, and a mass or a volume of any of the other reagents are asked. Our first example is what mass of potassium chlorate must be heated to produce 90 cubic decimeters of oxygen at STP. So to answer this question is important to be able to write a balanced equation. I've already done that. Then write the mole ratio. 2 moles of potassium chlorate will give me 2 moles of potassium chloride and 3 moles of oxygen. Now the important mole ratio here is that of the potassium chlorate to the oxygen. Now they're asking for a mass and they're giving us a volume. And they say this is at STP. Now whatever they give us, we need to change that into moles. So they gave us 90 cubic decimeters of oxygen as being formed. I need to change this into moles by dividing by the molar volume at STP. So it's 90 divided by 22.4. So 90 divided by 22.4, 0.4 is 4.01785. So I'm going to say 4.02 moles. Now the trick is to change this into the moles of potassium chlorate by using the highlighted mole ratio. So I need to divide it by 3 and multiply it by 2. And that would give me, multiply by 2, divide by 3, 2.6785. So I'm going to say 2.8 moles. Change this to mass, it's moles times molar mass, so it's 2.68. I'm not changing the answer on my calculator, so my value might differ from yours. Now the molar mass of potassium chlorate is 122.5. 122.5. So multiply that answer by 122.5 and I get 328.125, which you can write as 13 grams. Our next example is on page 203. When electric current passes through molten, that's melted aluminium oxide, it forms aluminium and oxygen. So the first thing we need to do is write a balanced equation. Al2O3 is decomposed through a process of electrolysis into Al and O2. To balance this equation, I need to multiply this oxygen by 3 and the aluminium oxide by 2 and the aluminium by 4. So the mole ratio in 2.2. Calculate the volume of oxygen formed at 200 degrees Celsius. So the important thing to notice here, it's not at STP. So we can't use 22.4. in this calculation. Calculate the volume of oxygen formed at 200 degrees Celsius and a pressure of 300 kilopascals if 30 tons, 30,000 kilograms. Now to write this, it's 30 million grams. I'm going to use scientific notation. 3 times 10 to the power 7 grams of aluminium oxide is decomposed. So we need a mole ratio. 2 moles of aluminium oxide gives us 3 moles of oxygen. So we need to change the mass to moles. Moles is mass over molar mass. So it's this 3 10 to the 7 divided by, it's 2 times 27, 2 times 27 plus 3 times 16, that is 102, 102. Sure, that divides into 330 million, and you get, sure, 294,117.64, 294,117.65 mole. Right, to get the moles of oxygen that is required, you need to divide by 2 and multiply by 3. So times 3 divided by 2 equals. So this mole of oxygen here is 441,176.4706 moles. Wow, not at STP. So that means I need to go to my basic gas equations. So the ideal gas equation, PV equals nRT. And I need to remember that this pressure must be in pascals. So the pressure in pascals will be 30,000. So it's 3 times 10 to the power 5. The volume that we calculate will be in cubic meters times 441,176.47 times R is 8.314 times the temperature is 200 degrees Celsius, so it's 473 Kelvin. I get a volume of 5,783.12, and this would be cubic meters. Right. Example 3 is on page 202, where we have to calculate the total volume of gas in an enclosed reaction container upon the completion of a reaction where 100 cubic centimeters of hydrogen is mixed with 100 cubic centimeters of nitrogen. The reaction runs to completion. Now this actually belongs to our limiting reagent section, but I'll do it here. We need a balanced equation. Hydrogen reacts with nitrogen to form ammonia, and to balance the equation we need to multiply hydrogen by 3 and ammonia by 2. So 3 moles of hydrogen reacts with 1 mole of nitrogen to form 2 moles of ammonia. Now, the important thing to remember here is Avogadro's law, and that at the same temperature and pressure, equal volumes of gas will have the same number of particles. So the volume ratio would be exactly the same as the mole ratio. So if we start off with 100 cubic centimeters of hydrogen and 100 cubic centimeters of nitrogen, the nitrogen will be too much because they react in the ratio 3 to 1. So we need to determine how much of the hydrogen will react. All the hydrogen will react. 100 cubic centimeters needs a third of that. So a third of this is 33.33 cubic centimeters of nitrogen. That is what is needed for 100 cubic centimeters of hydrogen. If you take 100 cubic centimeters of nitrogen, that would need 300 cubic centimeters of hydrogen, which we don't have. So, and this will form double the amount of nitrogen, ammonia, so it's 66.66 cubic centimeters of ammonia will be formed. So at the end, how much hydrogen is left? 0 cubic centimeters is left because this will be used up. How much nitrogen will be left if 33.33 cubic centimeters is used? There will be 66.66 cubic centimeters after completion, and 66.66 cubic centimeters of ammonia was formed. So at the end, the total volume of gas is 66.66 times 2, which is 133.2 cubic centimeters. I better just check on my answer. What's 100 minus 33.33? It's, I should have said 7 there. And maybe I should have said 7 here. What to double up on that? 30, no, yeah, it's more or less right. Maybe this must be a 3, 30, yes. Thank you for watching. Okay, let's put another 3 there. Thank you for watching.